May 18, 2026, 3:47 a.m. UTC. A satellite picks up 1,200 degrees Celsius of thermal radiation directly beneath Thwaites Glacier, the largest and most unstable glacier on Earth. The eruption itself won't kill us. What will is what it's silently melting, the only ice shield standing between stable sea levels and the displacement of hundreds of millions of people. And here's what makes this so much worse: no sound, no seismic tremor, no warning. Nobody knows how long this has already been burning beneath Thwaites. Stay with me, because in the next 72 hours, we'll find out whether Earth's last ice shield is still holding. Let's get into it. Antarctica, May 2026. There is no sunrise here, not in winter. The sun dropped below the horizon weeks ago and will not return for months. This is the polar night, absolute and total. A darkness so complete it has a physical weight to it. The sky above the ice sheet is not dark blue. It is not charcoal. It is black in a way that city dwellers never experience, a black with no gradient, no ambient glow from distant civilization, no softening at the edges, just black, pressing down on 4.6 million square miles of frozen silence. Surface temperature -40 degrees Celsius. The wind moves across the ice sheet in long, toneless sweeps, carrying nothing, going nowhere. There are no trees to bend, no water to ripple, no animals to scatter. Just the wind and the ice in the dark, exactly as they have been for millions of years. From the outside, from any angle a human eye could reach, this place looks exactly as it always has: ancient, indifferent, asleep. At 3:47 in the morning, Coordinated Universal Time, the European Space Agency's Sentinel-6 satellite completes another passive thermal sweep across the Antarctic interior. This is routine. The satellite has done this hundreds of times across dozens of orbital passes, dutifully scanning the surface and subsurface thermal signatures of the ice sheet below, logging temperature gradients in columns of data that are, almost without exception, exactly what researchers expect to find: stable, consistent, cold. The kind of data that confirms nothing is happening, which is precisely what scientists want to see when they are watching a glacier the size of Great Britain sitting on top of a bedrock depression that reaches more than 2 kilometers below sea level. The data streams back to ground stations in quiet columns of figures. Most of them are boringly consistent. Most of them say nothing to see here. Move on. Then one pixel breaks. Not figuratively, literally a single unit of spatial data representing a discrete patch of ground at the central coordinates of Thwaites Glacier returns a thermal reading of 1,200 degrees Celsius. 1,200. The analysts stare at it. They check the timestamp. They check the sensor calibration logs. They look for the obvious explanations: electromagnetic interference from a solar event, a corrupted data packet somewhere in the transmission chain, a processing artifact introduced during image reconstruction. They run every standard diagnostic in the protocol. Each one comes back clean. The pixel holds 1,200 degrees Celsius is not a number that belongs in an Antarctic dataset. To put it in physical terms, 1,200 degrees Celsius is the temperature at which basaltic rock transitions from solid to liquid. It is the approximate surface temperature of freshly erupted lava flows at shield volcanoes like those in Hawaii and Iceland. It is a number associated with the interior of the Earth, with the upper mantle, with magma chambers, with the deep plumbing systems that feed volcanic eruptions. It has no business appearing in a thermal scan of an ice sheet where the surface temperature is -40 degrees Celsius and where 2.7 kilometers of glacial ice sit between the sensor and whatever is generating that heat. Within minutes of the anomaly being flagged, the data packet is being reviewed simultaneously by glaciologists at 3 separate research institutions across 2 continents. Everyone is looking for the error. Everyone wants the mundane explanation, because the alternative that the reading is accurate is a scenario nobody is prepared to process at 3:47 in the morning. They run the verification checks. They cross-reference against the previous 6 orbital passes. They pull the raw sensor data before any processing filters have touched it. The pixel holds every time at 1,200 degrees Celsius, directly beneath the central coordinates of Thwaites Glacier. Now here is where it stops being merely unusual and starts being deeply, fundamentally wrong. Across Antarctica, 2 seismic networks operate continuously, 24 hours a day, every single day of the year, regardless of season, regardless of weather, regardless of the polar night that makes the continent inaccessible to human researchers for months at a time. The first network is POLARnet, the Polar Earth Observing Network, a carefully distributed grid of broadband seismometers embedded into the bedrock across the Antarctic continent, specifically designed and positioned to detect the faintest mechanical disturbances propagating through the crust beneath the ice. These instruments are extraordinarily sensitive. They can detect a magnitude 0.5 tremor from hundreds of kilometers away. They were built to miss nothing. The second network is IDA, the International Deployment of Accelerometers, a global array of high-sensitivity seismic instruments with multiple Antarctic nodes. IDA instruments are capable of detecting not just conventional earthquakes, but the long-period, low-frequency oscillations that characterize magma movement deep within the crust. These are the signals that volcanologists worldwide have come to rely on as the earliest possible warning that something molten is moving somewhere it shouldn't be. Together, POLARnet and IDA form the most comprehensive seismic surveillance infrastructure ever deployed on a polar landmass. Between them, there is very little happening beneath the Antarctic ice sheet that they cannot detect. At 3:47 in the morning on May 18th, 2026, both networks are reading the same thing across every station, every sensor, every frequency band. Silence. Not reduced activity. Not a faint background murmur that might be explained away as noise from the West Antarctic Rift System going through a quiet phase. Not a degraded signal from a sensor that might have suffered weather-related interference. Silence flat, unbroken, absolute. The seismograms are clean straight lines. There is no harmonic tremor anywhere in the dataset. This matters enormously, because harmonic tremor is the geological fingerprint of moving magma. It is a sustained rhythmic vibration in the Earth's crust, typically oscillating at frequencies between 1 and 10 Hz that forms when molten rock forces itself through conduits, cracks, and channels in solid stone. The movement of magma through the crust generates friction, pressure differentials, and resonance effects in the rock walls surrounding the conduit, and all of those physical processes produce mechanical vibrations that propagate outward through the crust and are detectable by seismometers, sometimes hundreds of kilometers from the source. Harmonic tremor sounds, when the seismic data is converted to audio, like a deep, sustained hum, low, continuous, unmistakable to anyone who has spent time staring at volcanic seismograms. Every documented volcanic eruption in the scientific record surface or subglacial has been preceded and accompanied by harmonic tremor. Without exception, it is not an occasional feature of volcanic activity. It is a physical necessity. Magma cannot move through solid rock without generating the vibrations that produce harmonic tremor. The signal may be faint when the activity is deep and the volumes are small, but it is always there. Finding harmonic tremor in a seismic dataset is not diagnostic of a volcanic eruption. It is a precondition for one. Standard volcanic activity of the kind that precedes a surface eruption generates continuous seismic tremors registering between 2.0 and 3.5 on the Richter scale. These signals arrive days, sometimes weeks, before the eruption itself. They are the warning system that the Earth provides. They are what gives volcanologists time to issue alerts, coordinate with civil authorities, evacuate populations from danger zones, and position additional monitoring equipment to refine their eruption forecasts. Without harmonic tremor, without the seismic precursors that decades of volcanology have taught scientists to read, the entire warning infrastructure collapses. There is nothing to act on. There is nothing to see. The reading from Polanet and IDA on the morning of May 18th across every relevant station in the Antarctic network, 0.0 on the Richter scale. Not 2.0. Not a weak but detectable 1.5. Not even the faint 0.3 microseismic whisper that might be attributed to routine tectonic adjustments in the West Antarctic Rift System. 0.0. A thermal signature at 1,200 degrees Celsius registered by orbital satellite, and perfect unbroken geological silence in the crust below the source of that heat. That combination should not be physically possible. The physics of magma movement do not permit it. Rock does not heat to 1,200 degrees Celsius from volcanic activity without the movement of magma, and magma does not move without generating seismic signals. The two phenomena are inseparable. One cannot exist without the other, not under any standard model, not in any documented case, not according to any established understanding of how subglacial volcanic systems behave. And yet, to understand why 0.0 is more terrifying than any earthquake ever recorded on the Richter scale, you need to know what this place looks like when everything is normal. Thwaites Glacier covers 120,000 square kilometers of West Antarctica. Take a moment with that number, because square kilometers are easy to say and hard to feel. 120,000 square kilometers is approximately the total land area of Great Britain, England, Scotland, and Wales combined, laid flat on the polar ice sheet and swallowed whole without a trace. It is larger than the state of Ohio, larger than the entire country of Bulgaria. It is not a glacier in the way most people picture a glacier, a dramatic river of ice carving through a mountain valley, visible and photogenic. Thwaites is a vast, flat, featureless expanse of white. From the air, it looks like nothing, just whiteness extending in every direction to the limit of visibility and beyond. Average ice thickness across the glacier, 2.7 kilometers. In the deepest sections, where the bedrock beneath Thwaites sits more than 2 kilometers below sea level, the ice pressing down on that submerged rock is thick enough to stack nearly 9 Empire State Buildings on top of each other. The weight of that ice depresses the bedrock itself, pushing the underlying rock down into the mantle through a process called isostatic loading. The geology beneath Thwaites has been shaped by the presence of this ice over millions of years. The ice and the rock exist in a long, slow conversation with each other, a conversation that has been going on since long before the first humans appeared on Earth. Scientists have been listening to that conversation continuously since 1990, not casually, systematically, with a monitoring infrastructure that includes satellites equipped with synthetic aperture radar, GPS arrays drilled directly into the glacier surface to measure millimeter-scale movements in real time, airborne, ice-penetrating radar missions that map the bedrock geometry kilometer by kilometer beneath the surface, ocean floor sensor networks measuring the temperature and flow of the water circulating beneath the floating ice shelf at Thwaites' seaward edge, and ground-based seismometers recording the faint tremors that propagate through the rock below the ice. Thwaites has been studied more intensively than almost any other glacier on Earth, not because it is the most dramatic to look at, but because it is the most consequential if it fails. The arithmetic is straightforward and brutal. If Thwaites fully discharged into the Southern Ocean, global mean sea level would rise by approximately 65 centimeters, roughly 2 feet from Thwaites alone. But Thwaites does not sit in isolation. It acts as a structural buttress for the broader West Antarctic ice sheet, and its collapse would remove the physical support holding back neighboring ice masses. Conservative estimates suggest a full Thwaites collapse could ultimately drive more than 3 meters of global sea level rise when the cascading effects on surrounding ice are accounted for. 3 meters. That number, applied to the current geography of human coastal settlement, affects over 1 billion people. It erases cities. It ends nations. It is the kind of number that appears in the conclusions of peer-reviewed papers under careful qualified language, but which means, in plain terms, a reorganization of where human civilization is possible on this planet. So scientists watch Thwaites carefully, constantly, with everything they have. And what 35 years of watching has shown them is a glacier that moves in slow, measurable, largely predictable rhythms. Normal sliding velocity at Thwaites approximately 4 kilometers per year. To be precise, the glacier's various tributaries and flow lines move at slightly different rates, but the central trunk, the main body of the glacier draining toward the Amundsen Sea, flows at roughly 4 kilometers per year on average. That is fast by glaciological standards. Most of the world's glaciers move at rates measured in tens or hundreds of meters per year, not kilometers. 4 kilometers per year is what scientists call a fast-flowing glacier, but it is consistent. The rate has been measured, mapped, and tracked with satellite radar since 1990. And while it has been gradually accelerating over recent decades in response to warming ocean water eating at the glacier's underside, the acceleration has been incremental and has followed modeled projections reasonably well. 4 kilometers per year is the drumbeat of Thwaites. It is the number that anchors every projection, every model run, every estimate of how long the glacier has before it reaches critical thresholds. The temperature at the base of the ice, the contact interface between the glacier's underside and the underlying bedrock, sits between -2 degrees Celsius and -5 degrees Celsius under standard measured conditions. Those numbers are critical. At those temperatures, the basal ice is frozen, or nearly frozen, to the rock beneath it. Frozen basal ice creates friction. Friction resists sliding. Friction is the physical mechanism that regulates how fast Thwaites moves toward the ocean. Lose the friction, warm the base, introduce liquid water at the interface, reduce the contact force between ice and rock, and the glacier's velocity can increase dramatically. The basal temperature is not just a data point, it is one of the primary control variables governing the stability of the entire system. Below the ice, the West Antarctic Rift System produces its own consistent background seismic signature. The rift system is a major tectonic feature, a zone of active crustal extension stretching roughly 3,000 kilometers across the West Antarctic plate. Comparable in scale to the East African Rift Valley, and like all active rift systems, it generates minor but regular seismic activity. Small tremors register routinely on the Paulinet network magnitudes between 0.5 and 1.2 on the Richter scale, appearing several times per week at various locations across the rift. These tremors have been characterized exhaustively. Researchers know their typical frequency content, their likely source depths, their spatial distribution along the rift system, and their seasonal patterns. They are expected. They are cataloged. They are, in the language of seismology, part of the baseline, the predictable background against which any anomalous signal must be measured. Put it all together, and the picture is of a sleeping giant enormous in scale, slow in rhythm, consistent in behavior. A glacier with a heartbeat that scientists have been listening to carefully for 35 years, sliding at 4 kilometers per year. Basal temperature between -2 and -5 degrees Celsius. Minor seismic activity several times a week, perfectly in keeping with the regional tectonic baseline. A system under stress? Yes, undeniably, increasingly, but changing on timescales that have, until now, allowed for measurement, modeling, projection, and at least the theoretical possibility of preparation. That is what normal looks like at Thwaites. That is the 35-year baseline, the established rhythm, the known heartbeat of the glacier that scientists around the world have built their sea level projections around, their coastal planning frameworks around, their entire understanding of how much time humanity has left to act around. But on May 18th, that heartbeat suddenly vanished, and what replaced it is something far more frightening. Imagine you place a thick iron plate over a gas burner. The flame underneath is running at full intensity, orange and blue, and furious, pushing heat upward into the metal at temperatures that would instantly char anything biological. But the top surface of the iron plate is still cold to the touch, still solid. No crack, no rupture, no explosion, no sound at all. Just heat transferring upward through the metal, degree by degree, invisible and silent, until eventually, not dramatically, not with a bang, the iron begins to soften, then to glow, then to flow. That is an aseismic subglacial eruption. That is what is happening beneath Thwaites. The terminology requires unpacking because it sounds, on first encounter, like a contradiction. Subglacial eruption, a volcanic event occurring beneath a glacier, is a well-documented phenomenon. Scientists have studied subglacial eruptions in Iceland, in Chile, in Antarctica itself. But those eruptions all share a defining characteristic. They are loud. They announce themselves through the crust in the language of harmonic tremor, seismic bursts, and ground deformation that instruments can read from hundreds of kilometers away. The word aseismic, attached to subglacial eruption, means the opposite of all that. It means a volcanic event generating measurable heat, enough heat to register at 1,200 degrees Celsius through 2.7 kilometers of ice on an orbital thermal sensor, while producing no detectable seismic signature whatsoever. Silent heat, invisible fire, an eruption that the Earth's own warning system cannot see. To understand how this is physically possible, you have to think about what magma is actually doing in this scenario, and, crucially, what it is not doing. In a conventional volcanic eruption, magma forces its way upward by fracturing rock. It breaks through fault planes, widens existing cracks, carves new pathways through solid stone. Every fracture event generates seismic energy. Every instance of magma physically displacing rock produces vibrations that propagate outward through the crust. This is noisy work. The Earth makes sound when it breaks, and magma breaking its way to the surface is, from a seismic perspective, extremely loud. The harmonic tremor that volcanologists listen for is precisely this: the accumulated acoustic signature of rock fracturing, magma flowing, pressure building and releasing in rapid rhythmic cycles as molten material forces its passage upward. At Thwaites, the evidence 1,200 degrees Celsius above 0.0 on the seismographs below suggests something different is happening. The magma is not punching through solid rock. It is not fracturing its way upward. Instead, the heat appears to be transferring through an existing pathway, one that does not require breaking anything new, one that is, in fact, lubricated in a way that absorbs and dampens the mechanical energy that would otherwise become seismic signal. That pathway is water. Beneath Thwaites, as beneath much of the Antarctic ice sheet, there exists a complex and only partially mapped network of subglacial lakes and interconnected water channels. These are not frozen features. They are pools and rivers of liquid water, trapped under immense pressure between the base of the glacier and the bedrock below, kept liquid not by warmth from above, but by the combination of geothermal heat from below and the pressure of kilometers of ice pressing down from above. The largest of these subglacial lakes beneath the West Antarctic ice sheet contain volumes of water comparable to some of the Great Lakes of North America. They are connected by a plumbing system of subglacial channels that can route water across hundreds of kilometers of bedrock, entirely invisible from the surface. If magma has intruded into a region adjacent to or beneath this subglacial water network, the physical consequences are unlike anything that happens in a conventional volcanic system. The magma does not need to fracture rock to transfer its heat. Instead, it heats the water directly, superheating it, converting it to high-pressure steam in localized zones, driving convective circulation through the connected lake network that distributes thermal energy across a far wider area than the intrusion itself occupies. The water acts as a thermal intermediary, carrying heat from the magma source to the ice base across a distributed interface measured not in meters, but in kilometers. And here is the critical detail. Water absorbs seismic energy. A body of liquid, especially one held under high pressure between two solid surfaces, acts as a mechanical damper, a shock absorber at geological scale. Vibrations that would propagate freely through solid rock are attenuated, scattered, and dissipated when they pass through a saturated zone. The subglacial lake network beneath Thwaites, if it is acting as the intermediary for this thermal transfer, would simultaneously explain both the heat signal and the silence. The magma heats the water carries the heat to the ice, and the water, in doing so, swallows the seismic signal that would otherwise tell every instrument on the continent that something is wrong. This is the mechanism, and it is, from an engineering standpoint, an almost elegant trap. What it means physically for the glacier itself is where elegance ends and catastrophe begins. As the basal temperature at the ice-rock interface rises, driven by conducted heat from below and by the circulation of thermally elevated water through the subglacial drainage network, the frozen contact between the glacier's underside and the bedrock begins to melt. The ice that was previously frozen to the rock, providing friction, providing resistance, providing the mechanical drag that regulates the glacier's seaward flow, is converting to liquid. The interface is liquefying, and as it does, the friction coefficient at the base of Thwaites drops. Under standard conditions, the frictional resistance at Thwaites' base is one of the primary forces keeping the glacier's velocity at approximately 4 kilometers per year. Introduce a sustained layer of liquid water at that interface, warm, pressurized water that cannot easily drain away because the surrounding bedrock is already saturated and the physics change completely. The glacier is no longer sliding against rough, frozen rock. It is sliding on water, and ice on water, under the weight of 2.7 kilometers of glacier pressing down, does not move at 4 kilometers per year. It moves at 5 to 10 times that rate. 5 to 10 times. That is not a refinement of the existing trajectory. That is not an acceleration that fits within the models that currently inform sea level projections and coastal planning documents. That is a phase transition in the behavior of the glacier, a shift from slow, trackable, somewhat manageable movement to rapid, potentially self-accelerating discharge that the existing monitoring infrastructure was not designed to respond to in real time. The heat does not need to be dramatic to produce this outcome. It does not need to melt Thwaites from below in any dramatic or visible way. It only needs to be sufficient sustained and widespread enough to maintain a liquid layer at the ice-rock interface across a significant portion of the glacier's base. At that point, the glacier does the rest itself. Gravity does the rest. The slope of the bedrock beneath Thwaites, which dips downward toward the open ocean in exactly the wrong configuration for stability, does the rest. But this is not the first time our planet has witnessed this physical trap, and history shows the consequences have never been small. The year is 1991, Hudson Volcano, in the remote Asen region of southern Chile, begins an eruptive sequence beneath the ice cap that covers its summit. Hudson is not a famous volcano. It does not appear in the popular imagination alongside Vesuvius or Krakatoa. It is a remote, glacier-covered stratovolcano in one of the most sparsely inhabited corners of South America, and for most of its history, it has been easy to ignore. In August of 1991, ignoring it became impossible. The eruption that began beneath Hudson's ice cap was, in seismic terms, well announced. Tremors, harmonic signatures, ground deformation, the instruments saw it coming. But the consequences of the subglacial interaction between magma and ice still caught the region off guard in terms of sheer speed and scale. The eruption drove rapid, uneven melting of the overlying ice, releasing enormous volumes of meltwater in a short time frame. The result was a geological, a glacial outburst flood, a phenomenon specific to volcanic regions where subglacial melting produces more water than the drainage system beneath the ice can contain. When the pressure exceeds what the subglacial environment can hold, the water releases catastrophically, all at once, in a pulse of flood discharge that has no equivalent in non-glaciated volcanic systems. At Hudson in 1991, the geological carved through the surrounding landscape and swept away 200 square kilometers of terrain in 48 hours. 200 square kilometers, erased, not flooded, erased. The force of the water was sufficient to strip vegetation, soil, and surface geology from an area larger than many cities, redepositing it downstream as a chaotic fan of debris. It happened in 2 days. 5 years later, in October and November of 1996, the world got a larger demonstration. Grímsvötn is a volcanic system in Iceland, situated beneath Vatnajökull, the largest ice cap in Europe, covering approximately 8,000 square kilometers of the island's interior. Grímsvötn has a history of subglacial eruptions. Icelandic scientists have been monitoring it for decades and have developed substantial expertise in managing the consequences. In 1996, a subglacial eruption at Gjalp within the Grímsvötn system began melting ice from below at a rate that the subglacial lake beneath Vatnajökull could not accommodate. Over the course of several weeks, the lake filled. Then it exceeded the pressure threshold at which the ice dam at its outlet could hold. The geological that followed produced a peak discharge of 45,000 cubic meters per second. 45,000 cubic meters of water every second, roaring out from beneath the ice cap and across the Sander Plain toward the North Atlantic. To put that number in physical context, the Amazon River, the largest river on Earth by discharge volume, carries approximately 209,000 cubic meters per second at peak flow. The Grímsvötn Jökull, at its peak, was running at roughly 1/5 the discharge of the entire Amazon. It lasted approximately 2 days. It destroyed a major road bridge, deposited icebergs the size of houses across the Sander Plain, and reshaped the surface geography of southern Iceland in ways that are still visible today. Vatnajökull covers 8,000 square kilometers. Thwaites covers 120,000 square kilometers. Thwaites is 8 times larger than Vatnajökull, not 8 times larger in some marginal, academic sense. 8 times larger in terms of the total ice volume available to be mobilized if a subglacial thermal event destabilizes the basal contact across a significant fraction of the glacier's area. The subglacial water network beneath Thwaites is correspondingly larger, more complex, and more extensively connected to the marine environment at the glacier's seaward margin. If a Jökull-class event were to occur at Thwaites, if basal melting driven by a subglacial thermal source were to load the subglacial drainage system beyond what it could contain and release, the discharge figures would have no precedent in the recorded history of human civilization. No unit of comparison exists. The Grímsvötn event, which reshaped Iceland and made international headlines, would be a rough draft. There is one more detail that connects these historical cases to May 18, 2026, and it is the detail that keeps researchers awake. Hudson, 1991, preceded by clear seismic warning, harmonic tremor, ground deformation, detectable precursors that allowed scientists to characterize the eruption before its consequences arrived. Grimsvötn, 1996, preceded by clear seismic warning. The Gjalp eruption was detected seismically and monitored continuously from its onset, giving researchers weeks of lead time to prepare for the Jökullaup that followed. Every historical subglacial eruption that has produced documented large-scale hydrological consequences was preceded by seismic signals. Every single one. The warning system worked in every case the scientific community has studied in detail. The harmonic tremor arrived first, bought time, allowed a response. At Thwaites, on May 18, 2026, the warning system returned 0.0. No tremor, no precursor, no lead time, just a thermal pixel at 1,200 degrees Celsius, appearing without announcement, with no way of knowing how long it had already been burning before the satellite happened to look. The historical record tells us what subglacial volcanic heat does to glaciers. It tells us the scale of the consequences when a large ice mass and an active magmatic system interact. What it cannot tell us, because no case like this has ever been documented, is what happens when those consequences arrive without warning. And while scientists are wrestling with the question of why, there are other things happening simultaneously that nobody wants you to know about. The thermal pixel appeared on May 18th. That is when the instruments finally spoke loudly enough that no one could dismiss what they were hearing. But the story did not begin on May 18th. It began months earlier, in data that was collected, logged, reviewed, and in several cases, quietly set aside as anomalous but inconclusive. Individually, each data point had a reasonable explanation. Together, they form something that should have been impossible to ignore. March 2026. The GRACE-FO satellite pair, Gravity Recovery and Climate Experiment Follow-On, a joint NASA and German Aerospace Center mission that measures gravitational anomalies caused by shifting mass distributions on and beneath the Earth's surface, completes its monthly assessment of ice mass loss across the West Antarctic ice sheet. GRACE-FO does not measure ice directly, it measures gravity. When ice melts and flows into the ocean, the mass of the glacier decreases and the local gravitational field weakens slightly. The satellite pair detects that weakening by measuring tiny changes in the distance between the two spacecraft as they orbit in tandem. It is extraordinarily precise, sensitive enough to detect ice mass changes measured in gigatons. From orbit through 2.7 kilometers of glacier, the March assessment for Thwaites came back 23%, above the comparable figure from March 2025. Not a marginal deviation, not a number within the range of seasonal variability that researchers routinely account for when interpreting GRACE-FO data. 23%. The glacier had shed significantly more mass in that month than it had in the same month the previous year, and the previous year was already considered an accelerated year by the standards of the decade before it. The research team flagged it. They ran the processing again. The number held. They submitted it for peer review within the IMBIE, the Ice Sheet Mass Balance Intercomparison Exercise Coordination Network, requesting cross-validation from independent teams using different satellite data sets. The cross-validation requests were still pending when April arrived. In April 2026, analysts processing Sentinel-1 synthetic aperture radar imagery, the same satellite constellation that would later capture the dark zones over the thermal anomaly, noticed something in the data from Thwaites' eastern boundary. The shear margin, as it is formally designated, is the lateral edge where the fast-flowing central trunk of Thwaites meets the slower-moving ice on either side. It is a zone of intense mechanical stress, the geological equivalent of the seam, where two rivers moving at different speeds grind against each other. Shear margins crack, they develop rifts, fracture networks, and lateral fissures that propagate over time as the velocity differential between the glacier's core and its flanks continues to tear at the boundary. Scientists track these cracks as indicators of the overall structural health of the glacier. A shear margin that is cracking faster than expected is a glacier that is losing its mechanical coherence. The eastern shear margin had expanded by 8 kilometers in 6 weeks. 8 kilometers of new fracture propagation in 42 days. The previous year's rate, measured over the same 6-week window, was 4 kilometers. The rate had doubled. No one had changed anything. No dramatic warming event had been recorded in the ocean water beneath the glacier's floating ice shelf in that period. The acceleration arrived without an obvious external cause, and no one had a clean explanation for it. It was logged. It was reported in the internal bulletins that circulate among Antarctic research consortia. It did not make headlines. 4 days before the satellite anomaly, on May 14, 2026, the staff at McMurdo Station, the United States Antarctic Research Base on Ross Island, roughly 1,000 kilometers from Thwaites, noted something in the geothermal monitoring data from a local hydrothermal feature near the station. The water level in a geothermal pool had risen by a measurable margin above its baseline over the preceding 72 hours, and the temperature profile at depth had shifted in a way inconsistent with seasonal patterns. The duty scientist on the overnight shift flagged it in the station log. The assessment written next to the flag, probable sensor calibration drift, recommend recalibration on next maintenance cycle. It was not recalibrated. The maintenance cycle was not scheduled for another 3 weeks. On the morning of May 18th, the thermal pixel came in at 1,200 degrees Celsius. And approximately 6 hours after that reading was flagged, analysts running the overnight SAR imagery from Sentinel-1 noticed something that made them go back and stare at the data for a long time. Directly above the thermal anomaly, directly above the coordinates where the satellite had recorded temperatures consistent with basaltic magma, the radar return from the glacier surface was wrong. SAR imagery works by bouncing microwave pulses off the surface and subsurface of the ice and measuring the return signal. Ice has a characteristic radar signature that reflects its internal structure, the layering of annual snowfall, the density gradients at different depths, the presence or absence of liquid water. A dark zone in SAR imagery over a glacier means the radar signal is being absorbed rather than reflected. And the most common cause of anomalous absorption in glacier SAR data is the presence of liquid water within the ice column, disrupting the internal structure that normally produces a clean return. Liquid water inside a glacier where no liquid water should exist. The dark zone was not a single pixel. It covered an area of several hundred square kilometers, and it had not been present in the SAR pass from 6 days earlier. 5 separate events. March mass loss acceleration with no explanation. April, shear margin crack rate, doubling with no external trigger. May 14th, geothermal anomaly dismissed as instrument error. May 18th, thermal satellite reading at 1,200 degrees Celsius. May 18th, SAR dark zone over the same coordinates. Each one, in isolation, is a data point. Each one, in isolation, has plausible alternative explanations. A calibration error, a seasonal fluctuation, a processing artifact. Scientists are trained to find the mundane explanation first because the mundane explanation is right far more often than the dramatic one. That is not laziness, that is methodology. That is how you avoid generating false alarms that erode public trust and drain institutional resources. But methodology has a limit. The limit is when 5 independent anomalies from 5 different measurement systems across 5 different months all point at the same location on the same glacier at the same moment. That is not 5 coincidences. That is a pattern. To understand why these seemingly disconnected events connect to each other, we need to go to the deepest layer of the planet. Most people, when they think about Antarctica, think about the surface, the ice, the cold, the whiteness. They do not think about what is happening 300 kilometers below their feet, in the hot, slow, semi-fluid rock of the upper mantle, where the real forces shaping this continent have been at work for tens of millions of years. That is understandable. The surface is what satellites measure. The surface is what photographs show. The surface is what disappears when sea levels rise. But the surface is not where the story begins. To understand what may be happening beneath Thwaites, you have to go down. The West Antarctic Rift System is not a crack. It is not a fault line in the way most people picture a single, discrete fracture running through the Earth's crust like a hairline in porcelain. The West Antarctic Rift System is a structural feature 3,000 kilometers long and up to 1,000 kilometers wide, comparable in scale not to the San Andreas Fault, but to the East African Rift, the geological system currently in the process of tearing the African continent apart. It is one of the largest active rift systems on Earth, and it sits entirely beneath the Antarctic ice sheet, completely invisible from any vantage point accessible to human eyes, known only through remote sensing, geophysical surveys, and the painstaking work of scientists who have spent careers listening to what the rock beneath the ice is trying to say. A rift system forms when tectonic forces pull a section of continental crust in opposite directions. The crust stretches. As it stretches, it thins. As it thins, the rock below the upper mantle, which is not liquid but moves like an extremely viscous fluid over geological timescales, rises to fill the space created by the thinning crust above it. The thinner the crust becomes, the less insulation there is between the mantle and the surface. The less insulation, the more heat escapes upward, and rising mantle material, decompressing as it moves toward lower pressures near the surface, can begin to melt, generating magma from rock that was solid at depth but becomes liquid as it rises. This is how rift zones produce volcanoes, not through subduction, not through collision, but through the slow, relentless stretching of the crust until the mantle beneath it finds a way through. The West Antarctic Rift System has been doing this for at least 35 million years. It is not a dormant geological curiosity. Geophysical measurements confirm it is actively extending. The crust on either side of the rift is moving apart at measurable rates. The extension is ongoing, and the crustal architecture beneath West Antarctica reflects the cumulative effect of tens of millions of years of thinning. Beneath Thwaites specifically, the numbers are stark. Standard continental crust averages between 35 and 40 kilometers in thickness, a figure that applies to the great majority of the world's landmasses. It is the geological baseline against which crustal thinning is measured. Under Thwaites, geophysical surveys using seismic tomography and gravity data put the crustal thickness at between 17 and 23 kilometers. Not 35, not even close to 35. 17 to 23 kilometers of rock between the surface and the mantle beneath a glacier the size of Great Britain. The crust under Thwaites is less than half the continental average. In places, it is approaching the thickness of oceanic crust, the thin, dense rock that floors the world's ocean basins and which sits closest to the mantle of any crustal material on Earth. A 2023 study published in Nature Geoscience measured the geothermal heat flux, the rate at which heat flows from the Earth's interior upward through the crust beneath Thwaites, and reported a figure of 114 milliwatts per square meter. The continental average is approximately 40 milliwatts per square meter. Thwaites is sitting on a floor that is bleeding heat at nearly 3 times the rate of a normal continent. This is not unusual for a rift zone. This is, in fact, exactly what rift zones do. But 114 milliwatts per square meter, sustained over the enormous area of Thwaites, is a thermal input of significant magnitude, enough to maintain liquid water at the glacier's base, even without any additional volcanic activity, enough to keep the subglacial drainage network pressurized and active, enough to contribute meaningfully to the basal melting rates that influence how fast the glacier flows. This is the geological context that existed before May 18th. The elevated heat flux, the thin crust, the active rift system. These were all known. They were factored into models. They were accounted for in projections. Scientists were not surprised by the existence of geothermal heat beneath Thwaites. What the models did not account for what no model had been asked to account for, because no one had seriously gamed out the scenario, was what happens if the thinning crust beneath an active rift system, already running at 3 times normal heat flux, develops a localized intrusion event. A pocket of magma pushing upward through the thinned rock, not breaking through to the surface, not producing a conventional eruption, but stalling at the base of the glacier and releasing its heat directly into the subglacial water system. Think of it this way. The system is a pressure cooker, an enormous one, with a floor that has been getting progressively thinner for millions of years, and a heat source below that has been running at high intensity the entire time. The ice above is both the lid and the contents. The water network at the base is the mechanism by which heat distributes through the system. Everything about the physical architecture of the West Antarctic Rift System beneath Thwaites was already configured, already primed, for exactly the kind of thermal event that the Sentinel-6 satellite detected on the morning of May 18th. The rift system did not spontaneously become dangerous on that date. It had been building toward this configuration for a very long time. May 18th is simply when the configuration produced a signal large enough to see. But a hot pressure cooker does not necessarily explode. The question is what happens when all of the systems inside it start synchronizing with each other. There is a concept in glaciology called marine ice sheet instability. It does not appear in news headlines often. It does not have the immediate visceral force of words like eruption or flood or collapse. But among the researchers who study ice sheets for a living, it is the term that ends conversations, the term that, when it comes up in a conference room, makes people put down their coffee. Marine ice sheet instability describes a specific physical condition, a threshold state in which the retreat of a glacier's grounding line becomes self-sustaining and irreversible without any further external forcing. The grounding line is the boundary where the glacier transitions from resting on bedrock to floating on seawater. It is the hinge point of the entire system. On the landward side of the grounding line, ice is grounded. It sits on solid rock, its weight pressing down, friction holding it in place. On the seaward side, ice is floating. It has lifted off the bed. It is buoyant, and it is no longer constrained by friction with the bedrock below. The grounding line is where those two regimes meet, and its position determines how much of Thwaites is actively draining into the ocean versus how much is still held in place by the rock beneath it. The geometry of the bedrock beneath Thwaites is what makes marine ice sheet instability relevant here. Unlike most continental ice masses, which rest on bedrock that slopes upward toward the interior, Thwaites sits on a retrograde bed. The rock beneath it slopes downward as you move inland, away from the ocean. The further back you go, the deeper the bedrock drops below sea level. This matters because of what happens when the grounding line retreats. If warm ocean water gets underneath the ice and melts it back, the grounding line does not just move to shallower ground, it moves to deeper ground, which means more of the glacier is now exposed to ocean water at its base. which means more melting, which means the grounding line retreats further, which means more exposure, which means more melting. A self-reinforcing loop, a feedback that, once initiated past a critical threshold, does not require any additional warming to continue. The physics drive it forward on their own. Between 2024 and 2025, measurements from airborne radar surveys and underwater autonomous vehicles operating beneath Thwaites' floating ice shelf confirmed that the grounding line had retreated into a region of deeper retrograde bed, not approaching that region, in it. The grounding line of Thwaites is now positioned in the geographic zone where marine ice sheet instability is not a future risk. It is a present condition waiting to be triggered. That is the first pressure point. The second comes from the ocean. The Amundsen Sea, which receives Thwaites' ice at its seaward margin, has been warming. The data collected by Argo floats, research vessel surveys, and ocean floor sensor moorings consistently shows that the water intruding beneath Thwaites' floating ice shelf, circumpolar deep water, a warm, salty mass that originates in the deep Southern Ocean, is running approximately 1.2 degrees Celsius above the temperature baseline measured a decade ago. 1.2 degrees does not sound like much. Applied to a human body, it is barely a detectable variation. Applied to the underside of a floating ice shelf, thousands of square kilometers in area, sustained over months and years, it is an enormous and continuous thermal input. The rate of basal melting on Thwaites' ice shelf has been measured at between 50 and 100 meters per year in the most affected zones. The ice is being eaten from below by water that is warmer than it was, steadily, with no indication of reversal. That is the second pressure point. The third arrived on May 18, 2026, at 3:47 in the morning UTC, 1,200 degrees Celsius, rising through a thinned crust, entering a subglacial water network already pressurized by 3 times the normal geothermal heat flux. Heat from below, driven by a geological system that has been building toward this configuration for millions of years. 3 separate forcing mechanisms. 3 separate physical systems: geological, oceanographic, glaciological, each operating on its own timescale, each driven by its own dynamics, each generating its own data that researchers in different disciplines have been tracking in relative isolation. The geologists watch the rift system. The oceanographers watch the Amundsen Sea temperatures. The glaciologists watch the grounding line. They publish in different journals. They present at different conferences. The data streams exist in parallel. What happened in the months before May 18th is that these 3 streams began converging, not metaphorically, physically. The elevated geothermal heat accelerating basal melt reduces the friction at the ice-rock interface, which accelerates the glacier's seaward flow, which pushes the grounding line further into the retrograde bed, which exposes more ice space to warm ocean water, which increases basal melt from the ocean side, which further reduces friction, which further accelerates flow, each system amplifying the next, each forcing function increasing the sensitivity of the others. This is what synchronization looks like in a physical system. Not a single catastrophic event, a convergence of pressures, each individually manageable, combining into something that is not. The IPCC 6th Assessment Report. The most comprehensive and rigorously peer-reviewed summary of climate science produced by humanity put numbers to the consequence. If global mean sea level rises by 3.3 meters above current levels, approximately 1 billion people are living in zones that experience regular, chronic inundation, not occasional storm surge, not 100-year flood events. Regular flooding, the kind that makes land uninhabitable, that destroys agricultural systems, that forces the permanent relocation of coastal populations. 3.3 meters is the figure that crosses the threshold from manageable disruption to civilizational reorganization. Thwaites alone, fully discharged, contributes somewhere between 65 centimeters and more than 3 meters when cascading effects on neighboring ice are included. The range is large because the uncertainty is large, but the lower bound is already inside the range that reshapes the geography of human settlement. 3 forcing mechanisms pointing at one threshold, with consequences scaled to 1 billion people. And while the natural system is crossing its thresholds, the layer of defense we built to protect humanity, everything designed to watch for exactly this scenario, is thinning in ways that are no less alarming. 34 stations. That is the number of broadband seismometer installations that Polonet, the Polar Earth Observing Network, maintains across the Antarctic continent. 34 instruments distributed across a landmass of approximately 5.5 million square miles. Europe covers roughly 3.9 million square miles. Antarctica is 1.5 times larger, and the seismic network watching it has 34 nodes. If you spread 34 monitoring stations across 1.5 Europes, you get coverage that leaves enormous blind spots between each instrument regions where a seismic event of moderate magnitude could occur without any nearby station registering it at a useful signal-to-noise ratio, and where a low-amplitude event, like the geothermal activity at Thwaites, might produce a signal indistinguishable from background noise at the nearest recording site, hundreds of kilometers away. This is not a criticism of the scientists who designed Polonet. Deploying seismometers in Antarctica is genuinely difficult work. Instruments must survive winter conditions that reach -70 degrees Celsius, must operate autonomously for months without maintenance, must transmit data via satellite links through polar night. 34 stations represent years of logistical effort and significant international funding. The network was built to detect conventional seismic activity, tectonic events, standard volcanic tremor, the signals that all prior subglacial eruption science told researchers to expect. It was not built to detect an aseismic subglacial eruption because prior to May 18, 2026, there was no confirmed documented case of one at this scale to design against. The network is blind to exactly the scenario that is now unfolding. The monitoring gap goes beyond seismology. There is no research station within 200 kilometers of Thwaites' central coordinates capable of directly measuring basal ice temperature in real time. Direct measurement of the ice rock interface, the most critical variable in determining how fast the glacier is destabilizing, requires instruments drilled through 2.7 kilometers of ice to the bed. Installing such instruments requires multi-season field campaigns, specialized drilling equipment, and the logistical support of a major national research program. The closest such direct measurements to Thwaites' center come from the WAIS Divide Ice Core project, completed years ago and positioned at the periphery of the region of interest. What is happening at the base of the glacier right now? At the coordinates directly below the thermal anomaly that is not being measured by any instrument in the ground. Scientists are inferring it from satellites, from models, from data streams designed for other purposes. They are reading the inside of the system from the outside. This would be a manageable limitation if institutional response mechanisms could compensate for it with speed. They cannot. The Antarctic Treaty of 1959 established a framework for international scientific cooperation across the continent that has, by most measures, served its purpose well over 7 decades. It demilitarized Antarctica, it prevented territorial disputes from escalating, and it created a structure under which researchers from dozens of nations share access to one of the most scientifically valuable environments on Earth. But the treaty also created a data governance architecture that was designed for a world in which Antarctic research moved at the pace of seasonal field campaigns and annual journal publications, not a world in which orbital satellites return thermal anomalies at 3:47 in the morning that require a coordinated multinational response within hours. Sensitive scientific data from Antarctic monitoring networks does not flow directly to the public or even to the full scientific community on detection. It moves through institutional channels, national Antarctic programs, treaty secretariats, coordinating bodies with review processes built to ensure accuracy before dissemination. In normal circumstances, this is responsible practice. You do not want preliminary, potentially erroneous data-driving policy responses or public alarm. But in a scenario where the temporal window between initial anomaly detection and potential consequence may be measured in hours to days rather than months to years, a review process calibrated for annual publication cycles becomes a structural liability. On May 18th, 2026, the glaciologists who received the Sentinel-6 thermal data made a decision that had no precedent in the 67-year history of Antarctic research under the treaty framework. They bypassed the process, not through any formal waiver or emergency protocol. No such protocol exists for this scenario, but through direct, urgent personal contact with decision makers in the United States National Reconnaissance Office and the European Union's Pleiades NEO satellite program. The NRO operates a constellation of imaging satellites whose resolution and revisit capabilities far exceed anything available in the civilian scientific fleet. Pleiades NEO is the EU's highest resolution commercial imaging constellation. Both systems are, under normal circumstances, allocated to national security and commercial applications with scientific use granted only through formal request processes that take weeks. The glaciologists got them in hours. Both systems were redirected tasked to Thwaites' coordinates for high-resolution optical and multispectral imaging passes at the earliest available orbital opportunity. Military and intelligence satellite assets, redirected to a scientific emergency through informal channels, faster than any established protocol would have allowed. This has never happened before in the history of Antarctic research. In 67 years of international scientific collaboration on that continent, no event has moved researchers to break the institutional architecture of the Antarctic Treaty System to obtain military satellite coverage within hours of an anomaly detection. That fact alone tells you something that no data stream, no seismogram, no thermal pixel can communicate as clearly. The people who understand this system best, who have spent careers studying Thwaites, who know every model run and every measurement and every margin of uncertainty, those people, on the morning of May 18th, acted like this was a genuine emergency, not a concerning anomaly, not an event worth monitoring carefully over the coming months. An emergency. The kind that does not wait for the next review cycle. But before you start to panic, I need to tell you something directly that most other places won't. Let's be direct about something first. No, this is not a geophysical weapon. No classified military program is cooking the bedrock beneath Thwaites with directed energy. No, NASA is not hiding a bigger truth behind a wall of institutional silence. These explanations circulate because they are psychologically satisfying. They give the event an author, a motive, a human hand to point at. They transform an incomprehensible natural phenomenon into something that can, at least in theory, be stopped if the right people are exposed or the right officials are pressured. They are wrong, and they are wrong in a way that matters, because believing them redirects attention from the thing that is actually frightening. The reason no one saw this coming is simpler than a conspiracy and far more unsettling. Science has never seen this before. Not at this scale, not under this much ice. Aseismic subglacial eruptions are not a new concept. The theoretical framework exists. Researchers have modeled the conditions under which magma could transfer heat through a subglacial water network without generating conventional seismic signatures. Papers have been written. The physics is understood in outline. but understanding something in outline and being able to predict it quantitatively, knowing when, where, how large, how fast are entirely different things. No predictive model in the current scientific literature can forecast an aseismic eruption beneath more than 2 kilometers of ice with anything approaching operational accuracy. Not within orders of magnitude. The models do not exist because the calibration data does not exist. And the calibration data does not exist because this type of event, at this scale, in this geological setting, has never been directly observed and measured in real time before. This is the honest position, not a failure of effort, not a failure of intelligence. A genuine frontier, a place where the known ends and the unknown begins, and where the unknown has just announced itself with a thermal pixel at 1,200 degrees Celsius. And the frontier has specific edges. There are precise things that science cannot currently answer about what is happening beneath Thwaites right now. And those unknowns are not minor uncertainties at the margins of an otherwise clear picture. They are central. How long has the magma been moving before the Sentinel-6 satellite happened to capture the anomaly on May 18th? The satellite does not provide continuous coverage. Each orbital pass covers the relevant coordinates at intervals. The pixel that broke at 3:47 UTC was the first detection, not necessarily the first occurrence. The thermal event could have begun hours before that pass. It could have begun days before. There is no way to determine the start time from the data currently available, which means there is no way to calculate how much heat has already been delivered to the subglacial water network, how much basal melting has already occurred since the event began, or how far the process has already progressed before anyone knew to look. The volume of the magmatic intrusion is similarly unknown. 1,200 degrees Celsius at a specific coordinate tells you the temperature at the source. It does not tell you the physical extent of the magma body, how wide, how deep, how much molten rock is involved. A small intrusion at that temperature and a very large one produce the same satellite signature in a single pixel. The difference in consequence is not marginal. A small Damascene shallow intrusion may exhaust its thermal energy in weeks. A large, deep-seated intrusion connected to an active magma chamber in the West Antarctic Rift System could sustain elevated heat flux for years, and no one knows whether the heat is still rising or has already peaked. The single data point from May 18th captures one moment. Subsequent satellite passes may show the anomaly strengthening, holding steady, or fading. Each of those trajectories implies a dramatically different physical scenario. As of the 72-hour window, that trajectory is not yet established. These are not details at the edges. They are the variables that determine whether the event beneath Thwaites is a bounded local anomaly or the beginning of something that will not be reversible. There is one additional signal that researchers are watching with particular attention, and it has received almost no coverage outside specialist channels. The GPS stations positioned on bedrock outcrops around the periphery of Thwaites installations designed to track millimeter-scale horizontal movements of the glacier through the position of fixed points in the surrounding rock are also capable of detecting vertical movement in the bedrock itself. When a large mass of ice melts and flows into the ocean, the weight pressing down on the underlying rock decreases. Rock, freed from that load, rebounds upward slowly at first, then faster as the mass loss accelerates. This process is called isostatic rebound, and it is normally a geological timescale phenomenon, something measured in millimeters per year over decades, not something that registers detectably in real time. If the GPS stations around Thwaites begin showing anomalous upward displacement bedrock rising faster than the established rebound rate, faster than any seasonal variation, faster than any signal that can be attributed to known mass loss rates, that is the quiet alarm. That is the instrument telling you, without drama, without a flashing red light, that ice is disappearing from above it faster than the models said it would. Not in the future? Now. The GPS data updates continuously. The researchers watching it know exactly what the baseline looks like. Any deviation from that baseline in the 72 hours following May 18th will be the clearest real-time signal available for what is actually happening 2.7 kilometers below the surface. So if we look directly at the two scenarios that can emerge from here, this is what the science actually shows us. The more probable outcome, based on the information available at the 72-hour mark, is that this does not become the catastrophe that the worst-case physics permit, approximately 65 to 70% probability, by the assessment of researchers working with the current dataset, and that estimate is itself uncertain, generated from models that were not built for this scenario, calibrated against historical cases that are only partial analogs. Call it a working probability, not a confident prediction. The science does not currently support confident prediction in either direction, but 65 to 70% is the number most commonly emerging from the teams actively analyzing the data. In this scenario, the magmatic intrusion beneath Thwaites is a localized event, real, significant, but physically constrained. The magma has not broken through to the surface, and it is not connected to a large, pressurized magma chamber that can sustain elevated heat output over an extended period. Instead, it has intruded into a pocket of rock adjacent to one or more tunnels in the subglacial lake network, heating the water in those tunnels, converting some of it to steam, driving localized convective circulation that elevates basal temperatures across a bounded area. The heat source is real, the heat transfer is real, but the system has a ceiling. As the intrusion cools, as the magma releases its heat into the surrounding rock and water and loses its thermal energy, the temperature differential driving the convective circulation decreases. The superheated zones begin to equilibrate. The pressurized water generated by the localized melting finds pathways through the subglacial drainage network and drains toward the glacier's seaward margin, not in a single catastrophic pulse, but in a gradual distributed release that the existing drainage architecture can accommodate. The velocity of the glacier does not spike. The grounding line does not jump. The ice shelf does not fracture under a sudden surge of ice pressing from behind. Thwaites continues melting. That part does not stop. Even in this scenario, the glacier continues its retreat along the trajectory that existing models project the grounding line, retreating further into the retrograde bed. The ice shelf thinning from below as warm Amundsen seawater continues its work, the mass loss rate remaining elevated. The bounded event scenario does not restore the glacier to stability. It does not buy decades of additional time. It does not mean that the long-term projections are wrong. What it means is that the intrusion does not add a new forcing mechanism on top of the existing ones at sufficient scale to trigger the rapid, non-linear response that the worst-case physics describe. But even the good version, is not actually good in any meaningful sense. A localized thermal intrusion of this magnitude, sustained even briefly against the base of a glacier already running at 3 times normal geothermal heat flux, already sitting on a retreating grounding line, already losing mass at accelerating rates, that event moves the timeline. Every estimate of when Thwaites reaches critical thresholds is built on assumptions about the rate of external forcing. Add a new heat source, even a temporary one, and those assumptions change. The projections that currently frame how much time coastal cities have to adapt, how many decades remain before certain sea level benchmarks are crossed, those projections shorten. By how much depends on data not yet available. Current estimates for the acceleration in the bounded scenario range from 5 years at the conservative end to 15 years at the upper end. 5 to 15 years removed from timelines that were already described as urgent by every major climate assessment of the past decade. The good scenario still costs something substantial. It just costs it slowly enough that the loss is distributed across decades rather than concentrated into a single catastrophic event. But the second scenario, though its probability is lower, is the reason scientists are not sleeping tonight. The 30% probability is where the physics stops being manageable. In this scenario, the magmatic intrusion beneath Thwaites is not small and not bounded. It is connected directly or through the subglacial water network to a heat source with sufficient volume and thermal energy to sustain elevated output, not for days or weeks, but for months. The basal melting it drives is not localized to a tunnel or a pocket in the subglacial lake system. It spreads laterally through the pressurized water channels that connect the lake network across hundreds of kilometers of bedrock, upward, through conduction into the base of the ice column above, the liquid layer at the ice rock interface, the film of meltwater that, when present, eliminates the friction that keeps Thwaites moving at 4 kilometers per year, rather than something far faster, does not form in a patch and drain. It forms across a significant fraction of the glacier's base and stays there, sustained by continuous thermal input from below, with nowhere to go because the drainage system is already saturated. When that happens, the glacier does not gradually accelerate. It shifts. The physics of ice on a frictionless liquid surface under the weight of 2.7 kilometers of overlying glacier pressing seaward on a retrograde slope are not complicated. They are brutally simple. The sliding velocity of Thwaites, currently tracked by NASA's Intermission Time Series of land ice velocity and elevation, the system abbreviated as ITS-LA-EV, would move from its current rate towards something between 5 and 10 times that figure. The instruments would see it. Satellites tracking surface displacement would register the acceleration within days of the basal condition changing at sufficient scale. This is the trigger. Everything after it follows from the physics. Step 1. The grounding line already positioned in the retrograde bed. Already in the configurations that makes marine ice sheet instability not a future risk, but a present one, collapses rapidly. Rapidly here does not mean instantaneously. It means months to 2 years, which is instantaneous by the standards of glaciological change, but catastrophically fast by the standards of any human institution designed to respond to sea level rise. As the glacier accelerates seaward, it carries more ice mass past the grounding line per unit of time. More ice crossing the grounding line means more ice transitioning from grounded to floating, which means the grounding line itself retreats further into the deeper retrograde bed, which exposes more ice base to the warm Amundsen seawater circulating beneath the floating shelf, which accelerates the basal melt from the ocean side, which reduces the backstress that the ice shelf exerts on the grounded ice behind it, which allows the grounded ice to accelerate further. The loop closes. Marine ice sheet instability activates not as a projection in a model run, but as a physical process unfolding in real time, and once it activates past the critical threshold, the geometry of the retrograde bed defines. No external intervention stops it. The glacier will drain. The question becomes only how fast. Step 2. The Thwaites ice shelf. The floating extension of the glacier that reaches out into the Amundsen Sea beyond the grounding line, buttressing the flow of ice from behind, loses its structural foundation. Ice shelves maintain their integrity through a combination of lateral support from the bedrock walls at their edges and the back pressure generated by the ice that has already discharged into the ocean ahead of them. When the grounded glacier behind the shelf accelerates dramatically, the increased flux of ice pressing into the shelf from the inland side overwhelms the shelf's structural capacity. Simultaneously, the retreat of the grounding line removes the pinning points, the bedrock highs and ridge features that anchor the shelf's underside and prevent it from moving freely. A shelf that loses its pinning points and receives a massive increase in ice flux from behind, does not thin gradually. It fractures. The calving events that result from this fracture sequence would have no precedent in the observational record of Antarctic glaciology. The largest documented calving event in the satellite-era iceberg, a 68, which calved from the Larsen C ice shelf in July 2017, produced a berg approximately 5,800 square kilometers in area, roughly the size of Delaware. That event was large enough to generate international coverage for months. In the chain reaction scenario at Thwaites, the ice shelf fracture does not produce one iceberg the size of Delaware. It produces multiple, potentially dozens, of discrete ice masses calving in rapid succession as the structural integrity of the shelf fails progressively across its entire area. The Southern Ocean south of 60 degrees latitude receives an amount of ice, discharged in a period of months rather than centuries. That has no equivalent since the end of the last ice age. Step 3. Physics does not permit that much mass to enter the ocean that quickly, without consequences that travel outward from the source. When a large ice mass, a berg of sufficient size and thickness, calves from a glacier and strikes the ocean surface, it generates a displacement wave. The mechanics are similar to those of a submarine landslide, which is one of the most efficient known generators of tsunamis, a large mass moving rapidly into a body of water, displacing that water faster than it can flow out of the way, producing a wave that radiates outward from the impact zone. A single large calving event generates a local wave. Multiple large calving events in rapid succession across the entire front of a fracturing ice shelf thousands of kilometers wide generate a series of waves that do not stay local. The Southern Ocean is not enclosed. It connects without interruption to the Pacific, the Atlantic, and the Indian Oceans. Waves generated in the Amundsen Sea propagate northward toward New Zealand, across the Pacific, toward Chile, along the South American coast, toward South Africa, across the South Atlantic and Indian Ocean. The travel time from the Amundsen Sea to New Zealand's coastline at standard tsunami propagation speeds through deep ocean water is approximately 12 to 18 hours. To the Chilean coast, comparable. To South Africa, slightly longer. These are not estimates constructed for dramatic effect. They are the outputs of standard tsunami propagation models applied to source coordinates in the Amundsen Sea. The wave heights that reach populated coastlines depend on the total calving volume and rate variables that, in this scenario, are not yet determined, but the direction and timing are not uncertain. The geometry of the ocean basins makes them fixed. Step 4 is the one that does not arrive in 12 to 18 hours. It arrives over years and decades, but it arrives with a finality that makes it, in some ways, the most consequential step of all. If the chain reaction scenario unfolds, if marine ice sheet instability activates irreversibly, if the ice shelf fractures, if Thwaites discharges into the Southern Ocean at a rate driven by rapid basal destabilization, rather than the slow trajectory currently built into sea level models, the contribution to global mean sea level rise accelerates dramatically. Not the 60 to 100-year timeline that current projections describe. The IPCC's sixth assessment report, working from models that assumed no aseismic subglacial eruption at Thwaites on May 18, 2026, projected Thwaites' sea level contribution across the 21st century. Those projections assumed the grounding line retreat and ice discharge would unfold on the timescale of decades. In the chain reaction scenario, that timescale compresses an additional 0.6 to 1.2 meters of global mean sea level rise not in 100 years, but within a single human generation. Put a human face on those numbers. Mumbai, 14 million people in the city proper, 21 million in the metropolitan area, much of it built on land that sits within 2 meters of current mean sea level. Dhaka 22 million people in a city on a delta system that is already sinking at rates of up to 1 centimeter per year, where seasonal flooding already displaces hundreds of thousands annually, and where a permanent sea level increase of 0.6 meters does not create a flood. It creates a new coastline that erases significant portions of the metropolitan area. Bangkok, 10 million people, built on soft alluvial sediment that has been compressing for decades under the weight of the city, where the land surface is already below sea level in parts and is held back only by a system of flood barriers and pumps that was not designed to operate against a baseline sea level 1 meter higher than when it was built. Ho Chi Minh City, Jakarta, Amsterdam, which has kept the North Sea out for centuries through an engineering infrastructure that is extraordinary by any historical standard, but which was calibrated against a sea level that no longer exists in this scenario. Miami, built on porous limestone that seawater moves through laterally, regardless of what barriers are placed on the surface above it, where the water table is already responding to current sea level, and where a further rise of 1 meter does not need to come over the seawall. It comes up through the ground. These cities are not hypothetical casualties in a distant future. In the chain reaction scenario, the timeline that places their populations inside the range of serious, chronic, infrastructure-destroying inundation compresses from something that planners could theoretically prepare for across generations to something that arrives within the professional lifetimes of the engineers who would have to respond to it. So now, in the 72 hours ahead and the weeks that follow, we need to know where to look to find out which scenario we are actually in. The next 2 to 4 weeks are the window. Not because anything will be definitively resolved in that period. The full trajectory of what is happening beneath Thwaites will take months to become unambiguous. But within 2 to 4 weeks, 5 specific data streams will show enough signal to determine, with reasonable confidence, whether the event is tracking toward the bounded scenario or whether the indicators of something larger are beginning to accumulate. These are not obscure signals. Several of them are publicly accessible. If you know where to look, you can watch them yourself. The first signal is the GPS data from 2 specific stations, THUR and LTHWE. These are bedrock GPS installations positioned near the periphery of Thwaites, part of the broader Antarctic GPS network, and they report vertical displacement of the bedrock surface with millimeter-scale precision. Normal isostatic rebound at these stations, the slow upward movement of rock relieved of glacial weight over decades, runs at measurable but modest rates consistent with the established mass loss trajectory. If the data from THUR or LTHW begins showing upward displacement exceeding 5 millimeters per week, a rate inconsistent with normal seasonal variation and inconsistent with the baseline rebound rate established over years of continuous measurement, that signal means one thing: ice mass is disappearing from above those stations faster than any current model predicted, not faster than the bounded scenario. Faster than any scenario that was on the table before May 18th. That reading, if it appears, is the quiet alarm that the GPS network is capable of sounding, and it will appear in the data before it appears in any press release. The second signal is the SAR imagery from Sentinel-1, the synthetic aperture radar satellites operated by the European Space Agency as part of the Copernicus Earth Observation Program. Sentinel-1 revisits Thwaites' coordinates every 6 days. The imagery is processed and made publicly available through the Copernicus Open Access Hub, free, downloadable, requiring no institutional affiliation to access. In the days following May 18th, analysts will be examining each new pass for changes in the dark zone that appeared coincident with the thermal anomaly. A dark zone that remains stable in area or contracts slightly is consistent with a bounded, localizing event. A dark zone that expands, that grows laterally across the glacier surface in successive imagery passes, indicating that the internal structural disruption of the ice is spreading rather than resolving is the surface signature of a basal process that is not contained. You do not need a research affiliation to load Sentinel-1 imagery and compare the dark zone extent between passes. The data is there. The comparison requires only attention. The third signal is the velocity data from NASA's ITS Live portal, intermission time series of land ice velocity and elevation, which aggregates satellite-derived glacier velocity measurements into near real-time maps of ice surface speed across Antarctica. Thwaites' central trunk currently flows at approximately 4 kilometers per year. The warning threshold is 5.5 kilometers per year, a figure that represents the upper limit of velocity consistent with the current forcing environment without an additional basal destabilization. If the ITS Live-Phi velocity maps show Thwaites crossing that threshold in the weeks following May 18th, the basal friction has changed, not gradually. Something at the base has shifted in a way that the instruments can see from orbit. 5.5 kilometers per year is not an arbitrary number. It is derived from the physical relationship between the known basal geometry, the current ice thickness, and the driving stress at the glacier's bed. Exceeding it means the denominator of that relationship, the friction term, has dropped. The fourth signal is the one that requires the most careful interpretation, because it is a paradox. Polonet returned silence on May 18th. That silence was the first and most alarming indicator that the eruption was aseismic, that the standard warning system had failed to see what was happening. In the weeks ahead, silence from Polonet is not necessarily reassuring, but tremor from Polonet is not reassuring either. If the seismic network begins detecting harmonic tremor in the frequency bands associated with magma movement, the 1 to 10 Hz sustained oscillations that are the geological fingerprint of molten rock forcing through conduits, that is not a sign that the situation is normalizing. It is a sign that the magmatic system is changing phase. Magma that was previously moving silently through the subglacial water network, damped by the liquid medium, has begun breaking rock. That transition from aseismic to seismic activity indicates the system is escalating, not retreating. Tremor from Polonet in the coming weeks means the event has entered a new stage. Watch for it, but do not interpret its appearance as evidence that the instruments have caught up with the situation and everything is now under control. The fifth signal is the simplest and the most decisive. WAIS, Divide Science Team. The research consortium managing the West Antarctic Ice Sheet Divide Project and the British Antarctic Survey both have scientific personnel monitoring this event in real time. The British Antarctic Survey maintains the longest continuous Antarctic monitoring program of any institution outside the United States, with infrastructure positioned across the continent and a communications protocol designed for exactly the kind of situation where rapid scientific coordination is required. Any formal public statement from either institution in the 72 hours following May 18th, any press release, any updated advisory, any statement to media that goes beyond routine scientific communication is the clearest possible signal that the internal assessment has moved past monitoring into something more urgent. These institutions do not issue emergency communications lightly. Their internal culture is, if anything, conservative in its public communications. A formal statement in that window means the people with the best data and the deepest institutional knowledge of Thwaites have concluded that the situation warrants breaking from standard protocol. Watch NASA Earth Data, the ESA Copernicus Open Data Portal, and the British Antarctic Survey's public communications channels. Not social media speculation. The primary sources. Now, what do you actually do with any of this? Do not panic. Panic is not a strategy, and it does not serve you or anyone around you. the bounded scenario remains the more probable outcome. And even the chain reaction scenario unfolds over months to years, not days. Nothing about the 72-hour window requires immediate physical action from anyone not directly involved in Antarctic monitoring or coastal emergency management. But do not look away either. Looking away is also not a strategy. It is a choice to let other people make decisions about information that directly concerns you. And it is a choice you make by default if you do not pay attention. If you live in a low-lying coastal area within 2 meters of current mean sea level, in a zone identified in your national flood mapping as at risk from sea level rise, this is a reasonable moment to review whatever personal preparedness thinking you have done, or to begin doing it if you have not. Not because flooding is coming tomorrow, because preparedness is not panic. Knowing your evacuation routes, understanding your local flood risk, having a clear sense of what you would do if conditions changed over the course of years or decades, that is not catastrophism. It is the same category of practical intelligence as knowing where your fire extinguisher is. You do not expect your kitchen to catch fire? You know where the extinguisher is anyway. Follow primary sources. NASA Earth Data publishes satellite-derived ice data. ESA Copernicus makes Sentinel imagery publicly accessible. The British Antarctic Survey maintains an Antarctic monitoring page. These are not difficult to find, and they contain the actual data, not summaries filtered through institutions with other priorities, not interpretations shaped by attention economics, not narratives constructed to maximize engagement. The raw information is available. Using it requires only the willingness to look directly at what it says and understand one thing clearly. Because it is the most important point in everything said here, preparation is not panic. Knowing is not catastrophizing. Looking at a difficult reality clearly, without flinching from what it might mean, and then making considered choices based on what you see, that is not fear. That is intelligence. The people losing sleep tonight are not the ones who turned away from the data. They are the ones who looked at it directly and understood exactly what the numbers mean. That is where you want to be. Not comfortable and unaware, clear-eyed and ready to act on what the next 72 hours show. You stayed until the very end, and that says something about you. It means you genuinely want to understand what's happening in the world, not just hear what feels comfortable. I truly appreciate that. What topic would you like me to explore next? The mechanics behind Arctic ice melt, how the global tsunami warning system actually works, or why climate models can be so inaccurate at times. Leave a comment below. I read every single one. See you in the next video, where we continue looking directly at the things the world keeps trying to blur.